Hello, this is Galen Pickett again, Cal State Long Beach, Physics 151. So today I want to talk to you about Section 10 of Chapter 4, the derivative form of the momentum principle. What happens when the dt that we're talking about is so small that using a finite delta is really not the appropriate thing to do. So here is the idea. I've got an object, it's got a position Ri, it's got a final position R final, and we have talked up till now about what the average velocity does for us. The average velocity times delta t tells me from where I started to where I ended. But if I let delta t get small, then the position of the final velocity is going to, the position of the final moment for the position of the object is going to get closer and closer to the initial position. So if delta t is half and the average is the same, you'd wind up here. If it was 1/100th, you would wind up something there. And if it's very, very small, the r initial and the r final would be almost zero. Let's see what the momentum principle would say this for the momentum update version. You would have P final is equal to P initial plus delta t times the force from the surroundings. Now, the final position, I can think of this momentum as something that depends on a continuous amount of time. The final momentum I could think of as the momentum evaluated at some t plus delta t. So that's the final time, t final. That's equal to whatever value the momentum has at the initial time, that's t, again, plus delta t times the force. Now, if I just take this expression and I let delta t goes to 0, delta t is exactly 0, this just says that p at the time t is equal to p at the time t. There's no information there, it's just the momentum is the momentum. So let me arrange this thing slightly differently. I'll say that the momentum at time t plus delta t minus the momentum at the time delta t is equal to delta t times the force. And now we have something a little more interesting. Now we've got not that the momentum is equal to the momentum, but as delta t goes to 0, I would have 0 is equal to 0. That doesn't mean that the force is 0, it's just that the delta t is so small that it doesn't really affect anything, and the final value of the momentum and the initial value of the momentum are both the same thing. And now let me divide both sides of this equation by delta t. The momentum at the time t plus delta t minus the momentum at the time t divided by delta t is equal to the force. Now, as I let delta t goes to 0, the force is just the value of the force. It's not necessarily 0, it's not infinity, it's just some finite thing. Over here I have something which is going to 0 in the numerator, but I also have something which is going to 0 in the denominator. And you might recognize this as the definition. If I put the limit outside here, the limit of delta t goes to 0, that is a finite difference formula. As the delta t goes to 0, I'm looking really at just what is the time derivative, d by dt, of this momentum as a function of time is equal to the force. And that is the infinitesimal time version of the momentum principle. And you'll use that. So the force tells you what is the rate at which the momentum of the system changes. That's what d by dt is, and you're taking a calculus class, or you have already taken a calculus class, so you know how to take a derivative. This was originally discovered by Isaac Newton under the special circumstances. So there's an approximation that the mass of the object is not time dependent, and the velocity is much, much less than the speed of light. If both of those things happen, then I can tell you an expression for what the momentum is. I would have d by dt m times v of t is equal to the force. Now, if the mass is not dependent on the time, then I can take it right out of the derivative symbol. So mass times the time rate of change of the velocity vector is equal to the force. And this is a special formula. It's got lots of names to it. It's called Newton's second law. The force from the surroundings is equal to the mass of the system times the acceleration of the system. And the acceleration is just defined to be the time derivative of the velocity, just the same way the velocity is equal to the time derivative of the position vector as a function of time. If I look at what that one looks like, take apart its finite difference, I would get v is equal to the limit as delta t goes to 0 of r of t plus delta t minus r of t divided by delta t, which is the same thing as the limit as delta t goes to 0 of delta r divided by delta t. And that's what the velocity is. I have here a measure of what is the average velocity over an infinitesimal amount of time. If I make delta t goes to 0, I get the instantaneous velocity. Likewise, if I make the delta t get very, very small, the time rate of change of the velocity is a vector known as the acceleration, and I get the force is equal to the mass times the acceleration. Newton's second law of motion. Newton's second law of motion is not fundamental. There's approximations and conditions. The mass cannot change with time, and the velocity is much, much less than the speed of light, even though, if you relax both of those things, d by dt, the momentum of the system, is still the force. That is true even in particle physics experiments.